Hello, welcome back. In this video we'll discuss the superionic conductors. The superionic conductors are a class of materials that conduct electricity by means of movement of ions in their solid phase. Superionic conductors are a class of materials that conduct electricity by means of movement of ions in their solid phase. The superionic conductors are a class of materials that conduct electricity by means of movement of ions in their solid phase. So essentially these are solids, and they have some similarities with the liquid electrolytes where the ionic conductivity takes place. Here also ionic conductivity takes place. Over the years, a number of materials have been investigated to exhibit superionic conductivity in solid phase, involving a wide range of materials including crystalline, polycrystalline, ceramics, glasses, composites, polymers, and polymer composites. The superionic conductors should possess certain characteristics. We shall discuss the characteristics of the superionic conductors. The first characteristic is the superionic conductors will have very high ionic conductivity, which is greater than or equal to 10 power minus 3 Siemens per centimeter or even higher. Superionic conductors will have very high ionic conductivity, that is greater than or equal to 10 power minus 3 Siemens per centimeter or higher. The second characteristic is these materials will have negligible electronic conductivity, that is less than or equal to 0.01% of ionic conductivity. Negligible electronic conductivity, that is less than or equal to 0.01% of ionic conductivity. Thirdly, these materials will have low activation energy, that is less than or equal to an electron volt. These materials will have low activation energy, less than or equal to an electron volt, for easy migration of ions. A large number of the ions of one species should be mobile, and also a large number of empty sites with equivalent activation energy should be available for hopping of ions between them. These materials should have a large number of ions of one species, should be mobile, and also a large number of empty sites with equivalent activation energy should be available for hopping of ions between them. While discussing the ion transport mechanism in a superionic conductor, we have said that the vacancy should have activation energy that is equivalent to that of the site from which the ion is migrating or hopping. And we have also said that the hopping depends on various factors like temperature, activation energy, and the lattice parameters. So we should have a large number of such ions that can move freely through the lattice, and also a large number of vacancies should be available within the lattice, and the vacancy should have the same activation energy as that of the lattice point from which the ion is originating. Under such conditions, the hopping takes place. So we have said a large number of ions of one species should be mobile. In this example, the species is A. A ions are available for hopping, not B. B cannot hop. Only one species of the ions they hop through the lattice. And also a large number of empty sites. These are the empty sites. Empty sites with equivalent activation energy should be available for hopping of ions between them. Only under such conditions, the ion can hop into this empty site or a point defect. The anion framework should be highly polarizable. And lastly, these materials should have physical and chemical compatibility with the anode and cathode of the desired electrochemical device or application. materials should be physically and chemically compatible with anode and cathode of the desired electrochemical device. The superionic conductors are classified basing on two parameters. Basing on the type of conducting ionic species, the superionic conductors have been classified into one group, and the other group is the host material. Basing on the host material that is used to develop the superionic conductor, the materials are also again classified. The first classification is based on the type of the conducting ionic species. For example, sodium, lithium, silver, etc. The second type is the type of the host material, such as crystalline, glass, composite, etc. While discussing the ionic conductivity in solid electrolytes, we have seen how the crystal structure imperfections can be used to explain ionic conductivity in solids. These crystal imperfections, they include point defects, linear defects, and the planar defects. However, in some materials, with the increase of the defects, one notices the decrease in the ionic conductivity. And these materials are generally the so-called solid acids, such as cesium bisulfate, with the general formula of MHXO4 and M3HXO4 taken twice, where M stands for cesium, rubidium, and ammonia, and X stands for sulfur, selenium. And we also have MH2X'O4, where X prime is phosphorus or arsenic. So these are all the general formulas of solid acids. And these materials, they exhibit structural changes upon heating. These changes in the crystal structure lead to a significant increase in the proton conductivity of the salts. Structural changes lead to a significant increase in the proton conductivity of these solid acids or salts. The proton conductivity properties are called as superprotonic properties, and these can be observed only at elevated temperatures. They are resulting from the existence of a dynamically disordered hydrogen bond network in the compounds, typically containing tetrahedral oxyanions. Superprotonic properties at elevated temperatures result from the existence of a dynamically disordered hydrogen bond network in the compounds, typically containing tetrahedral oxyanions. This is a crucial point here. The oxyanions structure should be tetrahedral. If you have tetrahedral oxyanions in these materials, one can see the superprotonic conductivity at the elevated temperatures. The proton conductivity essentially is also called as fast proton transport. The fast proton transport in these systems is realized by rapid reorientation of some specific structural units, such as the XO4 tetrahedra in the partially disordered structure of cesium bisulfate. In these systems is realized by rapid reorientation of some specific structural units, such as XO4 tetrahedra. In this diagram, we are showing the proton conductivity of the solid acids on the inverse of temperature along the x direction and a logarithm of the conductivity along the y direction. So a phase transition occurs here at high temperatures because it's inverse. On this side we will have the high temperatures and on this side we will have the lower temperature. On the higher temperatures, when you move to the higher temperature side, you notice that the super ionic conductivity is there. There is a sudden change in the conductivity. So this is a transition phase, and from here to here, the transition phase is very small. Higher conductivity at higher temperatures is the superionic conductivity. So at this temperature, the structural changes occur in the system. The ionic conductivity before the superionic phase is caused entirely due to the number and nature of the defects in the material. After the phase transition, the increased conductivity is mainly due to the individual structural units' cooperative behavior. So the superionic conductivity is due to individual structural units' cooperative behavior in the solids. If one introduces more defects, one can notice higher conductivity in the lower temperature region. However, when the defects are more, you see a small conductivity in the superionic conductivity phase at higher temperatures. So it is essential to have a pure solid acid phase to enable the highest possible proton conductivity. So pure solid acid phase is needed to have the highest proton conductivity. This figure explains the proton transport is largely facilitated only in one direction. Where the rotational degree of freedom is enabled, the proton transport is largely facilitated only in one direction. Where the rotational degree of freedom is enabled. The rotational degree of freedom is enabled in this direction, in the positive x direction. The oxytetrahedrons are rotating, giving rise the protons to move from left to right. These individual units, they combinedly will have a cooperative behavior for the total protonic conduction or the ionic conduction in the solids. In this video, we have started our discussion with the definition of a superionic conductor, and we have seen the various phases in which the superionic conductors can exist. We have seen the characteristics of the superionic conductors. We have seen how the conductivity can be explained. We have seen how the superionic conductors have been classified. We have seen the general formula of the solid acids. And in the case of solid acids, upon heating these materials, they exhibit structural changes, and the structural changes lead to significant increase in the proton conductivity of the solid acids. We have seen how the superprotonic properties at elevated temperatures they change. We have seen the fast proton transport in the system. We have plotted the logarithm of the conductivity along the y direction and inverse temperature along the x direction in Kelvin. We have seen the phase transition from conductivity due to defects to superionic conductivity. We have also seen the proton transport mechanism in the superionic conductors. Thank you.